Dear friends, today we are going to see a projectile motion in which air resistance is also taken into account. We consider a situation where the air resistance is proportional to the velocity of the particle. Before going with this, to consider this problem, let us consider the result for horizontal range in the case of a projectile motion without taking into account air resistance. The expression for horizontal range R is equal to u square sine 2 theta divided by g, where u is the initial velocity and theta is the angle at which the object is projected. During the First World War, when the Germans were attacking Paris, the capital of France, they were using a big gun known as Big Bertha. It had an initial velocity. It could impart an initial velocity u is equal to 1450 meters per second. And they projected it at an angle theta is equal to 55 degrees. Acceleration due to gravity is taken as equal to g is equal to 9.8 meters per second square. Substituting these values here, and when the calculation is carried out, we get the range as equal to 201.6 kilometers. But when the actual experiment was done, it found that the real R was only 120 kilometers. This is the huge difference between the calculated value and the value realized in actual practice. Why there is a difference like that? Because our derivation of R was carried out without taking into account air resistance. Assuming an air resistance which is proportional to the speed of the particle or the velocity of the particle, we can derive expressions for horizontal range. This is what is done in this lecture. First, as in the previous case, the angle of projection is theta and the initial velocity is u. We can write down the components of the initial velocity along the x direction as Vx0 is equal to u cos theta, and along the y-axis Vy0 is equal to u sin theta. Now, let us write the force equation for the x direction. In the x direction, the force equation will be m into d square x by dt square is equal to minus k times dx by dt, where dx by dt is the velocity in the x direction. The force is proportional to dx by dt with a minus sign because it is opposing the growth of velocity. It is against the direction of the velocity, the force. Therefore, this is the force equation for the horizontal case. This can be simplified and written as d square x by dt square is equal to minus k by m into dx by dt. Similarly, we can consider the vertical component and write down the differential equation to be satisfied by the object projected along the y direction. That is m into d square y by dt square is equal to minus k into dy by dt minus mg. Along the vertical direction, in addition to the air drag or air resistance, that is the force due to gravity, which is always acting vertically downward. All distances from the horizontal upward are taken as positive, and this force is always vertically acting downwards. Now, dividing throughout with m, we get d square y by dt square is equal to minus k by m dy by dt is minus g. In these two equations, k by m can be replaced with a new k, small k. K by m is equal to small k. With that, our differential equations assume the form d square x by dt square is equal to minus k into dx by dt. And the second equation, that is for the vertical component, this becomes d square y by dt square is equal to minus k dy by dt minus g. These are important basic equations, therefore I am writing them down here. D square x by dt square is equal to minus k times dx by dt, and d square y by dt square is equal to minus k into dy by dt minus g. This equation can be solved by rewriting it in terms of velocities. D by dt of dx by dt is d square x by dt square is equal to minus k into dx by dt. But dx by dt is vx, the component of the velocity in the x direction. That is, this becomes d by dt of vx is equal to minus k times vx. This can be integrated by variable separation method. dvx divided by vx is equal to minus k times dt. Integrating, we get ln of vx is equal to minus kt plus a constant of integration c. With this constant of integration c, we can fix this constant of integration c by applying the initial condition. When t is equal to 0, the component of velocity in the x direction is vx0. Making use of that, we can find this constant of integration c. That is, at time t is equal to 0, this becomes ln of vx0 is equal to c. This is substituted there. In this equation for c, we get ln of vx is equal to minus kt plus ln of vx0. Combining, we get ln of vx divided by vx0 is equal to minus kt. Exponentiating both sides, we get vx divided by vx0 is equal to e raised to minus kt, or vx is equal to vx0 e raised to minus kt. This can be written as another differential equation. Vx is dx by dt is equal to Vx0 e raised to minus kt. Integrating, we get x is equal to Vx0 e raised to minus kt divided by minus k plus constant of integration, say C1. Again, we can evaluate this constant of integration by applying initial condition to this equation. Initial condition is when t is equal to 0, x is equal to 0. When t is equal to 0, t is equal to 0, x is equal to 0. This is the initial condition. With that, we get 0 is equal to Vx0 divided by minus k plus C1, or C1 is equal to Vx0 by k. Now we can write the equation for x as equal to, x is equal to Vx0 e raised to minus kt divided by minus k plus Vx0 divided by k. Combining these two terms, we can write this as equal to Vx0 by k into 1 minus e raised to minus kt. This is the expression for the horizontal displacement or the x component of the position of the object at time t. X is equal to Vx0 divided by k into 1 minus e raised to minus kt. Now let us consider the vertical motion. For the vertical motion, we have already written down the differential equation, and that can be solved as follows. d square y by dt square is equal to minus k times dy by dt minus g. This is written as d by dt of dy by dt is equal to minus k into dy by dt minus g. But dy by dt is Vy. Therefore, this can be written as equal to d by dt of Vy is equal to minus k times Vy minus g, which is equal to minus of kVy plus g. Integrating, we can solve this by variable separation method. dVy divided by kVy plus g is equal to minus dt. Minus dt. Integrating, we get the left hand side as equal to ln of kVy plus g divided by k is equal to minus t plus a constant of integration, say C3. Again, this constant of integration can be evaluated by applying initial condition. When t is equal to 0, Vy is assuming the value Vy is 0. ln of k Vy0 plus g divided by k is equal to 0 plus C3. So, substituting for C3, we get ln of kVy plus g divided by k is equal to minus t plus ln of kVy0 plus g divided by k. Terms are taken to the left hand side, or first we multiply throughout with k and then take the second term on the right hand side to the left. We get ln of kVy plus g divided by kVy0 plus g is equal to minus kt. That is exponentiating both sides. kVy plus g is equal to kVy0 plus g e raised to minus kt. So we can write kVy as equal to kVy0 plus g e raised to minus kt minus g, or Vy is equal to kVy0 plus g e raised to minus kt divided by k minus g by k. Again, we can integrate because Vy can be written as equal to dy by dt is equal to kVy0 plus g divided by k e raised to minus kt minus g by k. Integrating y is equal to kVy0 plus g divided by k e raised to minus kt by minus k minus g by k times t plus C4, another constant of integration. With that, we can obtain an expression for y as a function of t, provided we calculate or we evaluate the constant of integration C4. Again, we can make use of initial condition. At time t is equal to 0, the y displacement, y is equal to 0. With that, we get 0 is equal to kVy0 plus g divided by minus k square. When t is equal to 0, this becomes 1, and the second, this term will be vanishing because t is equal to 0, plus C4. Therefore, C4 is equal to kVy0 plus g divided by k square. When this substitution is done here, we get y. Y is equal to k Vy0 plus g divided by minus k square e raised to minus kt minus g by k times t plus k Vy0 plus g divided by k square. These two terms can be combined and we can write this expression for y as equal to y is equal to kv y0 plus g divided by k square into 1 minus e raised to, this has a minus sign here. When this is pulled out, we get this k Vy0 plus g divided by k square into 1 minus e raised to minus kt plus, minus g by k times t. This is the expression for the y displacement at time t. Now, when will this displacement become 0? It can become 0 at two times. When t is equal to 0, this term vanishes. This term will become 1 and 1 minus 1 is 0. Y will be 0. There is another time, say capital T, at which also this y will become 0. That is known as the time of flight. 0 is equal to k Vy0 plus g divided by k square into 1 minus e raised to minus k t minus g by k times t. But capital T is the time of flight which we can find using this equation. How we find that? This is taken to the left hand side. G by k times capital T is equal to k Vy0 plus g divided by k square into 1 minus e raised to minus kt 1 minus e raised to minus kt. Expression for y is k Vy0 plus g divided by k square into 1 minus e raised to minus kt minus gt Further simplifying, we get t is equal to g by k is taken to the other side. We get this as equal to k by g into k Vy0 plus g divided by k square into 1 minus e raised to minus kt. One k here and the other k here gets cancelled. This becomes k Vy0 plus g divided by k g into 1 minus e raised to minus kt. This is a transcendental equation in t, and this can be solved by either by numerical techniques or by a graphical method. Once this t is found by some method like that, we can put that t value in place of the small t here, and that will give us the horizontal range, taking into account an air resistance which is proportional to the velocity of the particle. With this, we have seen how a problem in which air resistance is also taken into account, how we have proceeded is like this. We consider, as in the previous cases, we split up the motion into two components, one horizontal and the other vertical. Along the horizontal direction, there is only air resistance. There is no acceleration due to gravity or force due to gravity along the horizontal. In that case, we have written down the force equation, which was m into d square x by dt square is equal to minus capital K times dx by dt. For the vertical motion, we have written down the force equation like this: m into d square y by dt square is equal to, again, minus k times dy by dt minus m into g. Here we have to include the force due to gravity. When such two equations are set up, differential equations are set up, further simplification is effected by dividing each of them with m, and we get constant capital K divided by m. That is replaced with a small k. With that, we have obtained two differential equations which are listed here. D square x by dt square is equal to minus k into dx by dt, and d square y by dt square is equal to minus k into dy by dt minus g. Now we have to solve them, and we first solved the first of these equations, which is simpler, and we solved and found an x that is equal to x is equal to vx0 divided by k times 1 minus e raised to minus kt. The second equation is also solved along similar lines, and the result was found to be y is equal to ky0 plus g divided by k square into multiplied by 1 minus e raised to minus kt minus gt by k. Then what we did is, we find that the equation for y as a function of time has two zeros. For t is equal to 0, y is equal to 0. Another is, when at a time capital T, this expression becomes 0. By setting that is equal to 0, we solve for capital T. Capital T is equal to k vy0 plus g divided by kg multiplied by 1 minus e raised to minus kt. This is a transcendental equation which can be solved either graphically or by using a computer program and numerical techniques like Newton-Raphson method. Provided we know, we can use some numerical values for this k. So we have found that thus we can find the time of flight. Once the time of flight is known, we can substitute instead of t the time of flight here, and the x position can be found. This will give the horizontal range of the particle. Thank you.